Welcome to today's session on solving problem number 2140, solving questions with Brainpower. In this problem, we'll explore an intriguing challenge involving decision-making and consequences, where each action affects future outcomes. Let's dive in and uncover the best strategies to tackle it. In this problem, you are tasked with maximizing the points you can earn by solving questions from a given list. The questions are represented as a zero-index 2D integer array called questions, where each element contains two values, the points you earn for solving that question, and the number of subsequent questions you must skip if you choose to solve it. For instance, if a question has points _I equal to 3 and Brainpower _I equal to 2, solving that question would earn you 3 points, but you'd need to skip the next two questions. You also have the freedom to skip any question entirely without earning points, and your goal is to determine the maximum points you can collect by making optimal decisions. The input to the problem is this 2D array, and the output should be an integer representing the maximum points achievable. To understand this better, let's examine an example. Suppose the input array questions is 3, 2, 4, 3, 4, 4, 2, 5. Here, the first question offers 3 points and requires skipping the next two questions if solved. Solving it gives you 3 points, and you move directly to question 3, which offers 2 points. Adding these together gives a total of 5 points. This is the optimal solution for this example, as no other combination of solved questions yields a higher score. The output for this case would therefore be 5. Now, consider another example with the input questions equals 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. Here, the optimal strategy starts by skipping the first question and solving the second, which earns you 2 points and requires skipping the next two questions. You then move to question 4, which earns you an additional 5 points. The total score is 2 plus 5, which equals 7. This demonstrates how strategic skipping can lead to higher overall points. The output in this case is 7. Additionally, the problem comes with constraints such as ensuring the solution can handle up to 100,000 questions efficiently. There are also some edge cases to consider. For instance, if the input contains only one question, the answer is simply the points of that question. If the input size is very large, the solution needs to be efficient to handle it within the given time limits. In situations where all questions are skipped, the output will naturally be 0, since no points are earned. Another challenge arises when the Brainpower _I values overlap, requiring careful tracking of which questions are skipped to ensure correctness. At its core, this problem can be approached as a dynamic programming challenge. For each question, you decide whether solving it yields more points than skipping it and moving to the subsequent questions. By carefully managing these transitions, you can calculate the maximum points efficiently. To begin solving this problem, we first consider the brute force approach. The intuition here is straightforward. For each question, we make a binary decision: either answer the question or skip it, and then recursively explore all possible combinations of these decisions. If we decide to answer a question, we add its points to our total and skip the number of subsequent questions specified by its Brainpower value. On the other hand, if we skip the question, we simply move to the next one. While this approach ensures that we evaluate all possible outcomes, its complexity is exponential, growing as O(2 to the power of n, because we are essentially exploring all subsets of decisions. This makes it highly impractical for large inputs, especially when the number of questions, n, approaches 10 to the power of 5. Additionally, the recursion stack requires O(n) space, contributing to further inefficiency for larger datasets. Now, to address the inefficiencies of the brute force approach, we can use dynamic programming. The key insight here is that the problem has overlapping subproblems, which means we can reuse solutions for smaller subproblems rather than recomputing them repeatedly. Specifically, the decision at any question depends on the results of solving the subsequent questions. We use a 1D array, dp, where each entry dp, I, represents the maximum points obtainable starting from question I. The transition relation is based on two options. If we answer the current question, we add its points to the maximum points obtainable after skipping the required number of subsequent questions. If we skip the current question, the maximum points simply come from moving to the next question. The base case is straightforward: if we are beyond the last question, no points can be earned. By iterating backward through the questions array, we fill in the DP table efficiently, ensuring that each question is processed only once. This eliminates unnecessary recomputation and significantly reduces the time complexity. The dynamic programming approach provides a significant improvement in efficiency, reducing the time complexity to O(n), since each question is processed once. The space complexity is O(n) due to the DP array, but this can be further optimized to O(1) by using two variables instead of the full array. Given these advantages, we chose dynamic programming as our strategy. While the brute force method is conceptually simple, its exponential time complexity makes it infeasible for larger inputs. In contrast, dynamic programming is both efficient and scalable, leveraging overlapping subproblems to achieve linear time complexity. Additionally, it offers flexibility for space optimization, making it practical for real-world constraints. The trade-off is that dynamic programming requires a deeper understanding of recursion and state transitions, but this is a small price to pay for the significant performance gains. Overall, dynamic programming strikes an excellent balance between simplicity and efficiency, ensuring our solution runs within the problem's constraints, even when n is as large as 10 to the power of 5. In this problem, we are tasked with maximizing the total points we can earn by answering a series of questions. Each question has a specific point value, and if we choose to answer a question, we are required to skip the next k questions. This creates a decision-making process where, for every question, we need to decide whether to answer it or skip it. To understand this, we can visualize it as a decision tree. At each question, we have two possible choices: answering the question, which gives us its points but forces us to skip the next k questions, or skipping the question and moving directly to the next one without earning points. Each decision forms a branch in the tree, and the depth of this tree corresponds to the number of questions we have. This approach provides a brute force way of exploring all possible combinations of answers and skips to find the maximum points, but it is computationally expensive due to the exponential growth of possibilities as the number of questions increases. To formalize the brute force approach, we can define a recursive function, max_points index, which calculates the maximum points obtainable starting from a given question index. The base case for this function is simple: if the index exceeds the number of questions, we return 0, as there are no more points to earn. For the recursive case, we evaluate two options. First, if we answer the current question, we add its points to the result of calling the function on index plus k plus 1, effectively skipping the next k questions. Second, if we skip the current question, we simply call the function on index plus 1. The result for the current index is the maximum of these two options. Starting the recursion at the first question allows us to explore all possible combinations of answering and skipping. However, this approach has exponential time complexity, O(2 to the power of n), because each question doubles the number of decision branches. This makes it impractical for large inputs. To address the inefficiency of the brute force approach, we can use dynamic programming. The key insight here is that the brute force method repeatedly solves the same subproblems, such as calculating the maximum points from a given index. By storing the results of these subproblems, we can avoid redundant computations. We define a dynamic programming state, DP, I, which represents the maximum points obtainable starting from question I. The state transition logic is straightforward. If we answer question I, we earn its points and move to I plus k plus 1, so the contribution is points, I, plus dp, I plus k plus 1. If we skip question I, we simply move to I plus 1, making the contribution dp, I plus 1. The transition formula becomes dp, I, equals max, points, I, plus dp, I plus k plus 1, dp, I plus 1. For the base case, if I is beyond the last question, dp, I, is 0, as no points can be earned. This approach systematically builds up the solution by leveraging overlapping subproblems. To compute the dp values, we work iteratively from the last question backward to the first. This ensures that all future states, such as dp, I plus k plus 1, and dp, I plus 1, are pre-computed before being accessed. The final solution is stored in dp, 0, which gives the maximum points obtainable starting from the first question. This dynamic programming approach highlights several key insights. First, by eliminating redundant calculations through memoization, we achieve significant efficiency gains over the brute force method. Second, iterating backward through the questions ensures that all dependencies are resolved in the correct order. Finally, the skip constraint introduces a non-continuous dependency in the problem, which is effectively handled by dynamic programming. Together, these techniques transform an exponential time solution into a much more efficient linear time solution. Dynamic programming relies on efficient data structures to store and access pre-computed results. Here, we use a one-dimensional array, dp, of size n+1, where n is the number of questions. This array allows us to store the maximum points for each index, enabling constant time retrieval during computation. Additionally, we use another array, points, to store the point values for each question. This ensures that we can quickly access the point value of any question during the calculations. In terms of complexity, the time complexity is O(n), because we compute each dp, I, in constant time, iterating through the questions only once. The space complexity is also O(n), due to the storage required for the dp array. These optimizations make the dynamic programming approach both time-efficient and space-efficient for solving this problem. To better understand how the dynamic programming approach works, let's walk through an example. Suppose we have 5 questions with point values 3, 2, 5, 8, 1, and a skip constraint of k equals 2. We initialize the dp array with dp n equals 0 and compute values backward. Starting with dp 4, we calculate max 1 plus dp 7 dp 5, which equals 1. For dp 3, the calculation is max 8 plus dp 6 dp 4, resulting in 8. Similarly, dp 2 becomes max 5 plus dp 5 dp 3, which is 8. Next, dp 1 evaluates to max 2 plus dp 4 dp 2, giving 8. Finally, dp 0 is max 3 plus dp 3 dp 1, which equals 11. The final solution, stored in dp 0, is 11, representing the maximum points obtainable. This step-by-step computation illustrates how the reverse iteration and state transitions ensure correctness and efficiency in the dynamic programming approach. This solution uses dynamic programming to solve the problem efficiently. The dp array is initialized with zeros, where dp, I, represents the maximum points achievable starting from question I. The algorithm iterates through the questions in reverse order, from the last question to the first. For each question, we evaluate 2 options: 1, solving the current question, which adds its points and skips the required number of subsequent questions, or 2, skipping the current question and moving to the next. The maximum of these 2 options is stored in dp, I. Finally, dp 0 contains the maximum points achievable starting from the first question, which is returned as the result. This approach ensures we explore all possibilities while avoiding redundant computations, leading to an O(n) time complexity with O(n) space usage. This is the Java implementation of LeetCode problem number 2140, solving questions with Brainpower. The logic mirrors the Python solution, using a dynamic programming approach with a one-dimensional array dp to store the maximum points achievable from each question onward. Key differences include Java's explicit type declarations, the use of long for larger values, and Java's math.max for comparisons. This ensures equivalent functionality while adhering to Java's syntax and conventions. Here, we are working with the example where the questions array is 3, 2, 4, 3, 2, 2, 4, 0, 5, 0. First, we initialize the variables. The length of the questions array, n, is 5, and we set up a dynamic programming array dp with n+1 elements, all initialized to 0. This dp array will help us store the maximum points we can achieve starting from each question. We then start processing the questions in reverse order, beginning with the last question, question 4. Question 4 offers 5 points and requires skipping 0 subsequent questions. If we choose to solve it, we get 5 plus dp, 5, which is 5. If we skip it, we simply take dp, 5, which is 0. The maximum of these 2 options is 5, so we assign dp, 4, to 5. The dp array now looks like 0, 0, 0, 0, 5, 0. Next, we process question 3, which offers 4 points and requires skipping 0 questions. If we solve it, we get 4 plus dp, 4, or 9. If we skip it, we take dp, 4, which is 5. The better option is to solve it, so dp, 3 becomes 9. The DP array is updated to 0, 0, 0, 9, 5, 0. Then, we consider question 2, which offers 2 points and requires skipping 2 questions. Solving it gives 2 plus DP, 5, or 2, while skipping it gives DP, 3, which is 9. The best choice is to skip, so DP, 2, is set to 9. The DP array now becomes 0, 0, 9, 9, 5, 0. Now, we evaluate question 1, which offers 4 points and requires skipping 3 questions. If we solve it, we get 4 plus DP, 5, which is 4. If we skip it, we take DP, 2, which is 9. Skipping is the better option, so DP, 1, is set to 9. The DP array is updated to 0, 9, 9, 9, 5, 0. Finally, we look at question 0, which offers 3 points and requires skipping 2 subsequent questions. Solving it gives 3 plus DP, 3, or 12, while skipping it gives DP, 1, which is 9. Solving is the better option, so DP, 0, becomes 12. The final DP array is 12, 9, 9, 9, 5, 0. The maximum points we can achieve is stored in DP, 0, which is 12. In this example, the questions array is 1, 1, 2, 2, 3, 3, 4, 4. We initialize n to 4 and the DP array to 0, 0, 0, 0, 0. Starting with question 3, which offers 4 points and requires skipping 4 questions, solving it gives 4 plus DP, 7, which is 4. Skipping it gives DP, 4, which is 0. The better option is to solve, so DP, 3, becomes 4. The DP array now looks like 0, 0, 0, 4, 0. Next, we process question 2, which offers 3 points and requires skipping 3 subsequent questions. Solving it gives 3 plus DP, 6, or 3, while skipping it gives DP, 3, which is 4. Skipping is the better option, so DP, 2, is set to 4. The DP array updates to 0, 0, 4, 4, 0. Then, we evaluate question 1, which offers 2 points and requires skipping 2 questions. Solving it gives 2 plus DP, 4, or 2, while skipping it gives DP, 2, which is 4. Again, skipping is better, so DP, 1, becomes 4. The DP array is now 0, 4, 4, 4, 0. Finally, we consider question 0, which offers 1 point and requires skipping 1 subsequent question. If we solve it, we get 1 plus DP, 2, or 5. If we skip it, we take DP, 1, which is 4. Solving is the better option, so DP, 0, is set to 5. The final DP array is 5, 4, 4, 4, 0. The maximum points we can achieve is stored in DP, 0, which is 5. Now, in the third example, the questions array is 10, 1, 20, 2, 30, 3. We initialize n to 3, and the DP array is 0, 0, 0, 0. Starting with question 2, which offers 30 points and requires skipping 3 questions, solving it gives 30 plus DP, 6, or 30. Skipping it gives DP, 3, which is 0. The better choice is to solve, so DP, 2, becomes 30. The DP array updates to 0, 0, 30, 0. Next, we evaluate question 1, which offers 20 points and requires skipping 2 questions. Solving it gives 20 plus DP, 4, or 20, while skipping it gives DP, 2, which is 30. Skipping is better, so DP, 1, is set to 30. The DP array becomes 0, 30, 30, 0. Finally, we consider question 0, which offers 10 points and requires skipping 1 question. Solving it gives 10 plus DP, 2, or 40, while skipping it gives DP, 1, which is 30. The better choice is to solve, so DP, 0, becomes 40. The final DP array is 40, 30, 30, 0. The maximum points we can achieve is stored in DP, 0, which is 40. In analyzing the time complexity of our solution, the process begins with the initialization of the DP array. Since the array is of size n plus 1, this step takes n time. Next, we focus on the main loop, which iterates from the last question down to the first. This means there are exactly n iterations. Within each iteration, we access the current question's data, retrieve values from the DP array, and calculate the maximum between solving or skipping the question. Each of these operations is constant time, O1. Since the work done per iteration is constant and there are n iterations, the total time taken by the loop is O(n). Finally, returning the result stored in dp0 is a direct lookup that takes O1 time. When we combine all these steps, the overall time complexity of our solution is O(n). Now, for the space complexity, we start by considering the input. The question's array contains n elements, each consisting of two values, points and skip. Storing this input requires O(n) space. The DP array, which has n plus 1 elements, also contributes O(n) to the space complexity. Beyond these, the algorithm uses a small, constant amount of auxiliary space for variables like points, skip, and the loop counter, which adds O(1). When we combine all space considerations, the dominant factors are the input storage and the DP array, resulting in a total space complexity of O(n). To put this in perspective, let's compare our dynamic programming approach with a brute force solution. A brute force method would recursively evaluate all combinations of solving or skipping each question. Since there are two choices per question, this results in 2 to the power of n combinations in the worst case. Each recursive call performs O(1) work, leading to a time complexity of O(2) to the power of n. The space complexity of the brute force approach would be O(n) due to the recursion stack. In contrast, our DP solution avoids redundant calculations by storing intermediate results, reducing the time complexity to O(n), while maintaining a space complexity of O(n). This optimization highlights the significant efficiency gains of the DP method. To mathematically prove the time and space complexity of our solution, consider the for loop. It executes exactly n times, and each iteration performs a constant amount of work, O(1). Multiplying these, the total time complexity is O(n). On the space side, the DP array, which is of size n plus 1, contributes O(n), and the additional variables require only constant space, O(1). Therefore, the overall space complexity is O(n). When compared to the brute force approach, which has an exponential time complexity of O(2) to the power of n, our DP solution shows a dramatic improvement, scaling linearly with the input size. This makes it highly efficient and suitable for larger problem instances. Now, let's discuss some common mistakes that can occur when solving this type of problem. First, many people fail to consider all possible states or decisions. In dynamic programming problems, it's essential to think comprehensively about all the states your solution needs to track. Missing even one key state, such as skipping a question or considering edge constraints, can lead to an incomplete or incorrect solution. Next, inefficient recursion without memoization is another frequent pitfall. Without memoization, you might end up with a solution that repeatedly tackles the same subproblems, leading to exponential time complexity and making the solution impractical for larger inputs. Additionally, skipping edge cases is a classic mistake. Special cases, like handling an empty input, only one question, or scenarios with maximum constraints, are crucial to test thoroughly to avoid runtime errors or inaccurate outputs. Overcomplicating the solution is another issue. Sometimes the problem constraints allow for a simpler brute force or greedy approach, and unnecessarily forcing dynamic programming can make the solution more complex than it needs to be. Finally, ignoring trade-offs between space and time complexity can lead to inefficiencies. For example, using a full DP table when a rolling array might suffice can result in excessive memory usage, especially with larger inputs. Keeping these in mind can help you avoid common stumbling blocks and build more efficient solutions. To succeed in interviews or similar problem-solving scenarios, there are a few key insights to keep in mind. Recognizing patterns early on is critical. Problems that involve making decisions about skipping or including elements often map naturally to dynamic programming. Identifying this choice pattern early can save time and guide you toward the right approach. Also, pay close attention to constraints. For instance, if maximum skips or the input size is small, you might get away with a brute force solution. However, for larger constraints, optimization through methods like memoization becomes essential. During an interview, it's important to think aloud and clearly explain your reasoning. For example, articulate why you chose dynamic programming over a greedy approach and how your solution addresses edge cases. This demonstrates a structured thought process. Additionally, practice breaking problems into smaller subproblems. Clearly defining state transitions, how you move from one state to another, helps ensure your implementation is both correct and efficient. These tips not only improve your problem-solving skills but also make a positive impression in interviews. Let's look at some related problems and alternative approaches to solving them. LeetCode 198, House Robber, is a classic example where you maximize profit by deciding whether to rob houses, avoiding adjacent ones. Similarly, LeetCode 740, Delete and Earn, involves maximizing points with constraints, using a strategy that feels similar to this problem. LeetCode 121, Best Time to Buy and Sell Stock, focuses on making optimal decisions, though it's in a different context. And LeetCode 300, Longest Increasing Subsequence, is another problem that relies on decision-making and state transitions, making it a great way to build DP fundamentals. Now, in terms of approaches, brute force is straightforward but computationally expensive. It's only feasible for small input sizes due to its exponential time complexity for binary decision problems. Dynamic programming, on the other hand, offers efficiency for problems with overlapping subproblems, though it may come with higher space usage unless optimized. Greedy algorithms can sometimes work, but they're risky for problems where future decisions depend on earlier ones. Always verify correctness when using this approach. Recursive backtracking is helpful for exploring all possibilities, but without memoization, it often becomes inefficient. Understanding the trade-offs of these methods will help you choose the best approach for a given problem and set of constraints. Thank you for following along as we tackled problem number 2140, Solving Questions with Brainpower. We summarized the brute force approach and discussed its implications. Remember, practicing problems like this sharpens your ability to think critically about dependencies and optimization. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!